radiation properties of antennas, array antennas and reflector antennas is also well known. Now, here he has got several awards and recognitions. There are many more to come. These include Outstanding Engineer Awards, Special Invention Awards, Engineer of the Year Awards, etc. Here is a long list. I am not going to read those things. There are many. Now, his affiliation with the IEEE, he is a life fellow, as you know. He was a distinguished lecturer. He served as APS ADCOM member, and he also served as IEEE fellow, evaluation committee member, editor and associate editor of different IEEE publications. And with these few words, happy to invite Dr. Rao to deliver his lecture on antenna engineering for industry. Over to Dr. Rao.
Hear me now? Can you see my screen?
Yes. Dr. Rao, put in slide mode.
Yeah, I'm trying to do that. Okay. Thank you, Professor Anandan, for the nice introduction, and nice to hear you again. Hopefully we'll see you sometime. So my talk is on antenna engineering for industry. So I think most of the speakers are from industry. So what I want to share with the students and participants is how to become a good antenna engineer in an industry. And later I'll talk about some applications, not only for space. Recently I've been working on ground and also aircraft. So I'll show you some of my recent work. So I'm from Northrop Grumman, so I've been there for almost 10 years now. So this is my agenda. So I'll talk about future of antenna engineering. So future of antenna engineering is in the hands of students and young professionals. So it's very important that you guys become good engineers so that industries from space, defense, ground, wireless, and other applications can use you effectively. Then I'll talk about role of antennas, talk about antenna fundamentals a bit. I think that's very important. If you want to be a good antenna engineer, you cannot do anything without fundamentals. So if you have fundamentals, you can do a lot of things. You don't need to simulate. You can design very quickly. Only thing is, of course, you need to know the hardware knowledge as well. That is very important. So I'll talk about phased arrays and then briefly about reflector antennas, which are often used in satellites. I'll talk about some recent developments, and I'll talk about space antenna services, what are the various services, hardware and test as well. Because testing is very important. Unless you show by test, your customer won't believe. It doesn't matter how many theoretical simulations you do. I think unless you show by test, customers won't believe, and that's how you sell your products. And finally, some conclusions. So future of antenna engineers is very bright. So I think if you're working in the antenna field, I think it's very, very good. So antenna engineers are in very high demand in various industries, not just space, defense, ground, wireless, radars, MIMOs, RFID, biomedical, etc. We have actually a hard time finding antenna engineers because all all the companies are competing for limited resources. At least Northrop Grumman, we tried to hire about 100. Last year, we tried to hire about 50 engineers, but we got only, I think, about 7 or 8. And this year we're trying as well, but it's very hard because a lot of companies like Amazon, Facebook, and all these startups, I think they're paying a lot of money and getting all the young engineers, bright engineers. So I think we are finding it difficult, but I think we'll come up. So other thing I want to ask is, one of the questions is, are universities teaching the right skills to make engineers fit for the industry? So on the other hand, our industries, government agencies collaborating with universities so that they can directly hire the students once they become interns. Or so that's a scheme we have at Northrop Grumman. We get actually students as interns, and as soon as they finish the internship and they finish the course, we hire them. I think we hired, actually that's the only way we feel that we get engineers join our company because of the competition. So outstanding antenna engineer in industry is worth his weight in gold and more. So that's very important. No, you don't want to become just an ordinary engineer. You want to become very good engineer. So I think the industry values your contributions a lot. So antenna professionals, I think there are 3 types. So one is researchers. I think they mainly do publications. Academicians are their main part. This is very important. Their main job is teaching. And of course, they do some publications they need to do. Engineers, I think most of the students, I think they go into industries as engineers because that's where most of the jobs are. So that's to do that, I think you have to, main focus there is to develop products relevant to the industry. Focus is on the products. I think the main thing there is you don't worry about publications, and industry doesn't care too much about it, but it's out of your own interest you publish once in a while. Focus is on products and patents and trademarks. So it's very challenging career. If you want to be a good engineer, I think I recommend joining industry. Type of antenna engineers, of course, we get nowadays a lot of engineers, they want to do only software. I think some of them I was talking to like a couple of years back, they never touched any hardware, so that's not engineering. So you can do a lot of simulations, but unless you develop something hardware and test it and use on a program, I think it's not very good. So you need to know all the skills. You need to know the software. You need to know how to design the hardware, and then how to integrate the hardware with the rest of the payloads or rest of the RF circuits and other things, maybe systems. You need to test it and qualify it, and then you need to know how to write the proposals and work on the projects. So outstanding engineer requires all the above skills to make an end product suitable for the industry, whether it is for the space, or it is for defense, or it is for wireless, etc. And also the most important is you don't have infinite time to do the analysis, and you have a short schedule sometimes. So you have to deliver within schedule and within cost. You can't spend some of these projects are very short, like maybe within a year you have to design, complete, make, deliver, and test and fly it as well. So some cases, typically it is 18 months, but sometimes you have to do it within 12 months for the space. Academy versus industry. I think academicians tend to do a lot of different areas. They do a lot of things, different areas of research, etc. Whereas industry, I think once you join industry, I think you're married to the industry. So I call it dating versus marriage. So you cannot, once you join a space industry, you have to work on the products or areas that your industry is interested in. So that's very important. So it's just, you have to get married to the industry. So engineers need well-rounded knowledge and product development and leadership skills in the industry. So what is industry leadership? Of course, you need a vision. I think what exactly I think you're visioning, not just for now, for future. I think you have to see what is there 10 years from now. Sometimes you have to plan R&D and you have to sort of make things happen, see what others are doing. So then build and sustain a high performance team. So as a technical leader, you have to lead the team. So it's important you work with the team. If you are not able to work with the team, it's not good. So you have to motivate the team. You have to lead the team as well. And you have to take the ownership. Ownership means not only when it comes good, you don't take the credit. So when it actually you have to lead and you have to take the blame when it doesn't work. And when it works, I think you have to give the credit to the team. That's a quality of a good leader. And you need to lead with courage. Sometimes I think what you design may not work. So don't be afraid to fail. Of course, you can't fail too often. Once in a while is fine. I think it's risk is there in all the new developments, but don't be afraid to fail. Respond to challenges with resilience. So some challenges are very hard, but you have to be resilient and meet the challenges. So that's important. And act with speed. So speed is very important if you're working in the industry. So if you're late by about 1 month, I think you might be losing millions of dollars. So that's not very good. So basically you have to own. You have to become a model to your team, and you have to share your knowledge with the team members. Example of an outstanding engineer. I just give an example. It is my personal view, but I think it's a good example. So this person is only 34 years old. He has 10 patents already, 100 plus papers. Some of the papers are best paper awards. I think he got in IEEE APS. He wrote a textbook. Got many awards, including a recent Region 6 Outstanding Engineer of the Year award. So has made the key contributions to NASA, JPL, Mars Cube 1, Rain Cube, Europa Lander, and achieved more than most recognized persons of APS have achieved throughout their careers. So he's just 36 years old, 34 years old. So he works with passion. He works 24/7. So if he gets some doubt, I think he's not afraid to ask. He just calls you. He won't leave. He won't leave you unless he gets an answer. So that's how he works with. A true engineer and inspiring leader. He's the next speaker, by the way, Nazir Chahat from NASA JPL. Thank you, Nazir, for becoming a role model for all the youngsters. So work ethics, passion, persistence, and they make an engineer an outstanding engineer. So you have always worked with passion, and there's no 8 to 5 job and weekends. It's always 24/7. So sometimes you have to go in Saturdays, Sundays when your design is not working, whether it's under test, because a lot of technicians will be there. So you have to go, and you have to always be on the toes if you're in the industry. Next is the role of antennas on day-to-day communications. So we have seen satellites. I think on the left-hand side you see, on the right-hand side you have AVAX E3 antenna with a large phase array on the top, and on the bottom left I think we have B21, which is actually advancement of B2, which our company Northrop Grumman is making. So you can see that you don't see any antennas, but whole spacecraft body is antenna. So it's all stealthy, so you cannot see anything protruding outside. So Arecibo is the largest earth station antenna, at least probably a few months back. I think now it is collapsed during storm season there in Puerto Rico. So it's about 1,000 foot, and Chinese made about 1,500 feet antenna, and I think there is something in plan which is much larger than that. I think I don't want to say now, but hopefully somebody will during the presentations will talk about it. This is the Deep Space Network, one of them installed in Australia, 64 meters, operated by ISAW. So antenna, this is UAV, unmanned air vehicle. So this is also important because you can see that antennas will be there on the wings and protruding outside as well on the pods. So these constraints, all these applications, the constraints are different. So you have to know the constraints, and then only you can design proper antenna systems. So antennas are rise and years of any communication system. So next chart, it shows the geosynchronous orbit, where this is, I think, 2001. There's about 1,700 satellites in the geosynchronous orbit. So some are actually, the orbital arc is about 2 degree spacing, so that the reason for 2 degrees is ground antennas can separate the two satellites which are 2 degrees apart. And you can see a lot of satellites in a particular orbit. That's because of redundancy. Sometimes you have to put the redundant satellites higher in altitude, and when your satellite doesn't work, you have to bring it down, and so that you don't lose your TV services. So right now about 4,000 satellites are there, and a big congestion on the geostationary belt. So now we are looking into using higher bands instead of C-band, KU band, Ka band. We're planning to use V and W bands so that you get very large bandwidth, 5 gigahertz instead of 500 megahertz. And another advantage is you can reduce the spacing between the adjacent satellites from 2 degrees to about less than 1 degree. So that you can accommodate more satellites. And that will actually reduce the size of the ground antennas as well. So only thing is nobody knows what's the attenuation in V and W bands. So we are flying one experimental satellites. I think it's going to be launched soon, next month. So idea there is to launch it, experimental satellites, and there are 5 ground stations around CONUS, continental United States, wet area, rain area, dry area, etc., so that we can measure the attenuation constant and also the depolarization effects. So once I think these things are done, I think it will go into commercial practice soon. So this is what is a satellite. So satellite is nothing but a relay in space, so that its main purpose is to communicate between users on the ground and the ground to user to ground or ground to ground stations. So basic purpose is to provide communications on the ground. So geostationary satellite is at about 36,000 kilometers above the Earth altitude. Earth radius is 6,800 kilometers. So you can see the angle there is about plus minus 8.7. So with a small angle like that, you can get cover the whole Earth. Of course, you can see part of the Earth. To cover the complete globe, you need 3 satellites, one covering Asia, one maybe North America, one European coverage as well. So that way you can get a global coverage. And there are a lot of constellations like GPS, which have many more satellites to provide the global coverage. So what is difficult in satellites? Main considerations, what you see on the bottom left is thermal. So they have to operate at very hot and cold temperatures. So when the sun hits on the satellite, it goes up to plus 180 degrees or so. And when it is when the sun is on the back of the satellite, it gets very cold, goes to minus 160. So it's a basic 340 degrees difference. So you have to design all the components to withstand the thermal range. So there are sensitive components like filters, diplexers, etc. Sometimes even other components, polarizers. They are temperature sensitive. So when you design these components, you have to make sure that they withstand the temperature range, hot and cold. For example, filters, the passband moves around. So you have to make sure that you design the filters over a wide band, including thermal guard bands. So they have high power, sometimes 2 kilowatts power goes through because there's so many channels. 32 channels sometimes even 64 channels. So all these components, they have to withstand the high power. So you have to design components with enough gaps so that it doesn't cause multipaction. PIM is another consideration, passive intermodulation. So you have to make sure that PIM products are very low. PIM is basic phenomena where your channels will transmit channels with high power. They interact and provide the intermods. They generate intermods in the receive band. So receive LNA is very sensitive. So if these intermods, high intermods fall into that frequency, then it doesn't work. So you have to make sure the PIM levels are low. ESP, electrostatic discharge. So this is vacuum. Everything is vacuum. There is no atmosphere there. So anything, I think, charge, it collects the charge. So if it cannot discharge, then it blows up. For example, use of dielectric material. So that's why we rarely use dielectrics in space. So especially for high power applications, you can see most of the commercial satellites don't use any dielectrics. That's the main reason. Cross pole is very important because you want to increase the capacity of the satellite. You want to use both left-hand and right-hand polarizations, circular or BP and HP, vertical and horizontal for linear polarization, so that you can increase the capacity 2 times. So when you do that, you need to provide high cross-pole isolation between the 2 orthogonal polarizations. Typically, we need to meet 33 dB cross-pole isolation. This is not the best isolation or on-axis isolation. It is everywhere on the coverage. If it is CONUS coverage, continental US, at every point you have to make 33 dB copole to cross-pole ratio dB. So that's very tough. So to meet that, I think you have to design the systems with at least 38 to 40 dB cross-pole isolation, because there are measurement uncertainties. So when you measure, you want to prove that you're meeting 33 dB cross-pole isolation. And bandwidth is also very large, sometimes more than 60% bandwidth, because nowadays most of the antennas are common to both the transmit receive bands, which are spread over 60% bandwidth. So you have to meet very wide bandwidth too. So other thing is signal to noise ratio. So signal to noise ratio is ERP plus G over T. You can see the equation there. So you can divide ERP into gain of the transmit antenna and the power per channel going through transmit antenna. And gain of the receive antenna, T is the system noise temperature, which is negative. S is a big negative number. It's a space attenuation 4 pi r over lambda square. So that's both uplink and downlink. So that's each way it is almost like 220 dB negative. 10 log BW. BW is the bandwidth in hertz. So most of the numbers are large negative numbers. Only positive numbers are gain of the transmit antenna, gain of the receive antenna, and PI, which is small. It's not very big. So sometimes a lot of pressure on antenna engineers to maximize the gain. So sometimes quarter dB, half a dB makes a big difference in winning the proposal or not winning the proposal. So that's how important it is. So antenna is the most critical component of the satellite. So here in the block diagram, I show the uplink, which is actually a ground station is transmitting. So satellite is receiving, so that's called uplink. So then it down converts the uplink into downlink frequencies. Say if it is C-band, it receives at 6 gigahertz, down converts to 4 gigahertz, and the satellite transmits at 4 gigahertz. So that's called downlink. So both, and then there is also TT&C, command uplink, and telemetry downlink. So that link is mainly when the satellite is not in the orbit, but in the transfer orbit. That's only communication link. So if you lose that link, the satellite is lost. So though it is a small component because gain is not that high, it's very important part of the satellite. So these are satellite services. I won't go through that. Broadcast satellite service, this is for TV. Fixed satellite service, FSS, that is most of the countries have FSS. Intersatellite service, that is at V-band typically. So that's if you have a constellation of satellites, you want to communicate between satellites, so that's the link people use. Global positioning satellite, GPS, we all know about GPS. We can't live without it. So GPS satellites are very important. They are typically at low frequency bands. Mostly it's L band, L1, L2, L5. but S-band is also some people are using, like ISRO is using. Mobile satellite services, MSS. So that's important because it provides user to user on a mobile basis. So like trucks and ships and boats, etc. So they use. Personal communication is, I think that's the latest development is PCS. Sometimes it's called HTS as well, high throughput satellite. So these satellites carry very high capacity. Typical capacity of FSS is probably 5 to 10 gigabits per second. So whereas this high capacity satellites will have terabits per second capacity, which is almost 200 times more capacity. So they're used for high-speed internet and other services. So antenna design depends on satellite service and the coverage. So each one is different. So that makes it more interesting. So on the bottom side, you can see the spacecraft. When it's launched, it's basically launched in 3 stages. First stage, it takes the satellite to about 50 miles above the Earth. Second stage, it will take to about 100 miles and puts in the transfer orbit. So once you are in the transfer orbit, apogeic mode takes you to the right altitude. So all 3 stages, I think, you have to go through. And then it also has a ground station. So basically 3 components. One is a satellite, other is a launch vehicle, and other is a ground station. Just show you some video here to show the
advanced DHF payload, part of a system delivering unprecedented levels of assured network interconnectivity to rapidly deployable maritime, air, and ground forces, flexibly, where and when needed, immune from denial of service attacks, available in all levels of conflict. The payload puts the advanced in advanced DHF. A highly advanced digital processor serves as the switchboard in the sky, providing an order of magnitude increase in capacity versus Millstar, while supporting thousands of direct and rapidly reconfigurable flexible between use variety of operational platforms. The processor implements advanced security features to maintain both confidentiality and undeniable availability of U.S. international partners operating at multiple security levels and within separate security domains. As with Millstar, the advanced DHF payload supports user logon and communications at lower data rates, worldwide, without prior coordination, and in the most hostile environments imaginable. And like Millstar, the receive equipment, capable of accurately processing lower power spread spectrum signals in EHF band, with low probability of detection, stealthy communications in support of special operations. Payload's fast-hopping uplink and downlink phased array antennas can flexibly cover a wide area of the globe simultaneously with high capacities. While both Millstar 2 and Advanced DHF provide 6 1-degree spot beams which can be steered to anywhere in the satellite field of view via gimbal drive antennas, the Advanced DHF phased arrays support an additional 6 1-degree shareable spot beams, instantaneously steerable to any location within the satellite field of view. Operational planners have the option of allocating the capacity associated with each shareable beam among up to 4 separate regions within the satellite field of view, done on a hop-by-hop basis in milliseconds, transparent to users. From the ability to deliver high-capacity coverage to up to 30 separate regions, there still could be a need to provide higher capacity to isolated users outside of these regions. The advanced
advanced VHF satellite Northrop Grumman has built, and we have delivered about 6 of them. And currently we are working on the next version of advanced VHF satellite, which is probably more number of satellites, but more agile, and other things can handle more and provide more capacity. So, I think I'm showing different types of antennas high gain antennas. So they're generally 30 dBi to 70 dBi gain. So reflector antennas are frequently used. I would say probably 90% are reflectors. Lens antennas hardly used because of ESD problem. So people try to use dielectric lenses with ESD issue. Then they try to do waveguide lenses, but waveguide lenses are pretty heavy. And then to reduce the weight, you have to zone the lenses. When you do that, it becomes very narrowband. So I think it's hardly used. Array antennas, phased arrays, like I showed you, occasionally used, especially for military applications. So when you use agility and more flexibility and for anti-jamming applications, I think we use phased arrays because they're much faster. Medium gain antennas, they're 15 dBi to 25 dBi range. So generally they're horn antennas we use for global coverage or area coverage. Low gain antennas, they're used for TT&C when it's in the transfer orbit, but also you can use once it's in orbit to transfer the data to the ground. There are biconical antennas, waveguide antennas, horn antennas. So all of them are important depending on the application. So typical gains are between 5 dB and probably 0 dB sometimes, but most of the range is between 5 dBi and 10 dBi. Services, I think we talked about fixed satellite service, broadcast satellite service, which is basically high definition TV channels for national and local channels, mobile satellite service, inter-satellite links, and personal communication services. So radiation of satellite antenna depends on the spacecraft structure, antenna suit, and their coupling effects. So you design all these antennas, what you see on the top of top right corner individually, but when you put together, it doesn't work properly because there is coupling effects. The spacecraft is metallic body, so it scatters, diffracts. So you need to take all these things into account. So you design individual antennas and place them in the right places, and then you do the whole spacecraft scattering to ensure that there's no coupling problem, some high gain antenna affecting the low gain antenna like biconical antenna or so. So then you have to change the design, and once you finish, this takes about a month or two to do the complete analysis. So unless you do that, your design is not frozen. So I think that's a very important step. So some basics about antenna, how it radiates. So to radiate, I think antenna needs time varying currents. So these time varying currents produce electromagnetic waves. So basically transfers electric and magnetic fields you need. So there are four parts. I think you need a generator or transmitter or receiver. And then you need a transmission line, which might be a waveguide. And then you need a tapered transition. So that one is basically to match the waveguide impedance to free space impedance. And the taper transition is very important because that's basically your antenna. So that design depends on your directivity, what you need, or gain you need. So if it is high gain, then you need to have a bigger aperture. So that's basically the whole design is on the transition, taper transition region, not only providing the gain, but also providing the right match to free space. Typically, we design these systems with including transmission lines, everything. We design antennas with 25 dB return loss, not 10 dB. So you need that. So typical specs over temperature is about 20-22 dB. So to make that by design, you need to show at least 25 dB return loss. So this includes not just the antenna, it's a feed assembly, the reflector, the components like polarizers, the filters, diplexers, and the waveguides, etc. So all these things need to be included when you design the system. So we design these components, but then we need to integrate them and do the integrated design. Then only you can finalize. So directivity. So basically, you have always directivity or gain is referred to isotropic source. So isotropic source doesn't exist in practice. So it's only for theoretical calibrations. So it's a point source that radiates equally in all directions. In copole, no cross pole. So that's sort of isotropic radiator doesn't exist. So directivity is a measure of antenna. It's in dB. So basically, it depends how directive you can make the beam. So for example, on the omni beam, you can see the pattern is very circular or spherical. So if you want a directive antenna, so you have to make narrow beam. So the more narrow the beam is, you get more directivity. So basically, it depends on the size of the aperture size of the reflector, for example, or array size. And the gain is not the directivity. Sometimes people confuse gain and directivity. We don't care about the directivity, but we care about the gain. So directivity is basically what you compute. So that's basically relative to the aperture. So it doesn't have any losses. So I assume that you have certain tapered distribution. So how much directivity you can get in the far field. So that's basically directivity. So then you have to account for all antenna losses. So there could be reflector RMS, the feed losses, polarizers, the filters, diplexers, the transitions, etc. All these things need to be accounted, and also thermal effects. So with the temperature, I think cold becomes, the losses will increase when it's cold. So you have to analyze these losses, not just at ambient, but also over temperatures, whatever, minus 160 to plus 180. And polarization is very important. So vertical polarization is when E field is, it's a bit different from other definitions. For satellite applications, if the E field vector is along north-south, at the say conus within US, if it is north-south, then it's called vertical polarization. If the electric field vector is along east-west, it's a horizontal polarization. And we all know how the circular polarization is generated. We need two orthogonal vectors, vertical and horizontal, with equal amplitude and phase quadrature. So then actually the electric field vector rotates around. And if it rotates as it propagates clockwise, it's called right-hand circular. If it propagates anti-clockwise, it's called left-hand polarization. The sense is very important because at least two satellites, one Japanese satellites and one US satellites, they have the wrong circular polarization, and people cannot use it because the ground station can support only the one polarization. So we do at least polarization checks at least 6 times during the test campaign to make sure it has the right circular polarization or linear polarization. So I told you before it has uplink and downlink, so both links are important. So downlink is ERP, so that is how much is power is transmitted and gain of the transmit antenna. So and it has certain losses, so you have to, these losses could be sometimes maybe 1 dB to 1.5 dB. So you have to try to minimize these losses as much as possible to improve the gain. And then you have gain of the antenna, directivity of the antenna. So isotropic radiated power is power transmitted multiplied by the gain of the antenna, including all the losses. So G over T is also important. This is on the receive side. So G is the antenna gain and T is the system noise temperature. Takes into account the antenna noise temperature. So you have to calculate the antenna noise temperature also by integrating the patterns, because you have up to plus minus 8.7 degrees, you have hot earth, and beyond that it's cold sky. So I think it's not 290 degrees. People use that, but actually if you integrate the patterns and weight the patterns with the right temperature, either ground or sky temperature is about 5 degree Kelvin, ground is about 290. So it comes about less than 290, probably sometimes 250. Sometimes if the beam is towards the edge of the earth, it could be less than 200, 150 or so. So you have to calculate the antenna noise temperature, and then you can see the system noise temperature as well. Nice figure of the LNA plus including all the losses between LNA and the antenna. So both are very important. This is our typical system. I won't go through, but you can see on the right hand side ERP, they're in dBW, varies from 50 dBW to 46 dBW. The G over T is probably 1 dB minus 3 dB. So typically 3 to 4 dB variation you can expect within any shaped coverage. Otherwise, if it's more, then you're not designing properly. So there's some fundamentals about radiation from apertures. This is very simple. I think this is another example where your basic knowledge will help you a lot. So we all know that square apertures is sin x over x type distribution, where x is Ka sine theta, K is the wave number. And aperture has twice J1x over x, x is pi d over lambda sine theta. So d of the aperture. So J1 is the Bessel function of the first kind. So 2 is the normalization because J1x over x at x equal to 0 is 0.5. So just a normalization constant. So you can see the circular aperture has about 17.5 or 17.8 dB, and square aperture has about 13.2 dB. This is good, I think, for you can quickly estimate the size what you need from these, but of course you have to modify that with on the right hand side you can see the radiation from practical apertures. It's a bit different because you want to lower the side lobes pretty low. We want to typically 5 to 30 dB side lobes. So you can see the pattern. So on the right hand side top, so cross pole is also low we want. So you can model that also from these basic apertures. So the antenna directivity you can easily estimate from the aperture area of the antenna you're using times the efficiency. Typical efficiency with the reflector you get is about 80%. So EF is 0.8. So anything less than that, I think you have to check your design because that's not very optimal. So antenna gain also you can calculate very easily. So because this is normalized pattern, J1x over x, so 20 log of that will give you, sorry, I missed a factor of 2 there because on axis it's 0. So that gives you the patterns over at different angles. And 1 dB is basically loss from the aperture to the, that's a typical losses at C band and Ku band. At Ku band, it's slightly more, so about 1.5. So with this, you can estimate the gain very easily. And sometimes it doesn't have to be spot beam. If it is a shaped beam, you can also estimate very easily using gain area product. So, and these things are very important because if you're in the proposal stage, you don't have time to give the gain number because you need to give very accurately so that people don't over design or under design, especially the TWTA power, etc. So that's important. You have to give probably within actually you have to give in the meeting itself. You just take a calculator, calculate quickly, and tell them what the gain is going to be. So I think you should come close to, when you do the detailed analysis, you should come very close to probably within 0.3 dB or so. So this chart basically shows the difference between phased array and reflector antennas. I think we talked in advanced VHF, you have seen 15 antennas. Most of them are, 3 of them are one for uplink and 2 for downlink. So in a phased array, you need number of elements. So when you combine all these elements with proper phase, so you get a, say a 0 degree phase difference, you get a both side beam. And when you have a linear taper of the feed, of the phase, then you can scan the beam. So individual elements are broad. When you combine it, it becomes narrow. So you need, and then the variation, what you see is a scan loss. At both sides, you have say 40 dB. When you scan to 60 degrees, you're seeing about 35. So 5 dB is a scan loss there. So scan loss depends, you can calculate very easily. So that's the element roll off is basically the scan loss. So whereas if you go with the reflector, so the narrowest beam you can get is with a single feed. But when you combine the signal from array of feeds, you can make it broader. You can never make it narrow. So that's what shown on the top right side. You have element beams, a number of them. When you combine, it becomes a coverage beam or a broad beam with a lower gain, of course. So these are the two concepts. You can see phase array picture there and reflector. Basic difference is phased arrays are very narrow band and reflectors are very broad band. It can cover probably more than several octaves of bandwidth. You're limited only by the feed. So nowadays, feeds also you can make more than octave bandwidth, sometimes multiple octaves. So That's a very good property of the reflector. So it doesn't limit the frequency, and also it doesn't generate the cross pole. So that's very good. And also it's much cheaper. So phaser is cost anywhere between 10 million to 20 million, whereas reflector antenna costs about 1.5 million or so. So reflector, basically we talked about reflector assembly. So that's basically a reflector with a boom. So generally these are deployed away from the spacecraft panel on the east or west side. So you need a boom mechanism to hold the reflector in place. And then it is fed with a feed assembly. So feed assembly is basically the horn plus all the components that go with the feed, which includes polarizer, the OMT some cases, the filters, diplexers or multiplexers, whatever you need. And then there is a rigid waveguide and also a flex waveguide to take the feed to wherever the amplifiers are located. So what are the key parameters there? It's reflector size dictates the gain. Scan loss. And then so if you have circular polarization, the reflector doesn't depolarize, but it causes beam squint between LHCP and RHCP. Sometimes you have to use both, so you have to minimize the squint. It has a reflector, thermal paint to cover sometimes, deployment booms, mechanisms, sometimes gimbals on the back of the reflector to move them around. So important is surface accuracy. Typically, we design them with lambda by 100 surface accuracy, RMS. The losses have to be minimum. The cross pole is very important, and thermal stability is important because it has to work over wide thermal range. Feed assembly has all the horns plus OMT plus all the components. So its function is mainly to provide proper illumination on the reflector. So you have to optimize the illumination somewhere between, people use 10 dB as a standard, but I normally prefer to use at least 15 dB minimum illumination on the reflector on the transmit side, whereas receive is high frequency. It could be like 20, 22 dB, which is fine. So I think the idea is basically all the power illuminated by the feed has to be captured by the reflector with the minimum spillover loss. So that's why you use 15 dB illumination, tapered illumination. So the combination of reflectors and feed assembly are most crucial to satellite antennas. And you can shape the surface of the reflector. You can keep it paraboloid. You can shape it to generate the contoured beam or shaped beam to cover the country, such as India or US. These are the reflector basic geometries. You have on the left-hand side a center-fed parabolic reflector. We hardly use that nowadays because of the blockage, because you have all these rays coming from the feed illuminating the reflector when they're reflected back. Part of the area is blocked by the feed, so it causes gain degradation and increase in the side lobes. So offset reflector, when you offset it, then you don't have that problem. So, but then you have a lot of, sometimes a lot of cable actually or waveguide, so the losses will increase. So sometimes dual reflectors are used so that the feed is very close to the vertex of the reflector so that you can minimize the losses. So it can work on a Cassegrain where you have a hyperbolic subreflector, or it can work in Gregorian where you have ellipsoid subreflector. But these are basic geometries, but there are a lot of other new reflector configurations I think being developed on advanced reflector technology. So I think there are a lot of variations. People think reflector is just reflector, but it's not. So there are a lot of, you can shape them, you can use in a different configuration for depending on the applications. So you can make them very compact. So there are other developments I think going on. So this is how the offset reflector looks. So when you put the feed at the focal point of the reflector, it's called focal fed reflector. But some cases you need to defocus a single feed so that you can put a feed array. So it's called image plane optics. So basically you're defocusing so that your element pattern is broader so that when you place multiple beams, they overlap very well. So when you combine these signals, they combine very well as well. So that's image plane. Imaging reflectors are often used for mobile satellites and also for other applications, military applications. So you can calculate them very easily. I think you can either refer to this book or a couple of my papers. So efficiency is very important, E to F. So like I said, you need to design this at least 80% efficiency. So that depends on the taper. So you can calculate taper and then you can calculate the scan factor based on the offset reflector geometry. It's very easy. So you can even calculate the scan loss when you put a feed away from the focal in the focal plane or image plane. You can calculate that. And then you can see the efficiency versus horn size here in the curve. So when it's 2.2 wavelength, you get almost 80% efficiency. So this curve. So then if you use a multi-beam, multi-feed system, you can calculate the beam overlap as well as the side lobes as well. These curves are very handy, so one can use it. And some performance parameters. So the directivity versus d over lambda. Directivity on the right hand side, you have 3 dB beam widths in degrees. So as you increase the size of the reflector, so these are actually optimized for 80% efficiency. So you can use these curves for most cases. And in terms of phased arrays, I think we know that there are basically two geometries. One is a square grid. What you see on the right side, elements are arranged on a square, regular square lattice. And then hexagonal lattice, some people call it triangular, but it's actually hexagonal lattice. You see the element area covered by one element, it's a hexagon, so it's a hexagonal lattice. So both are used, and each one has its own advantage. If it is for satellite application for geostationary, we use hexagonal lattice because it reduces the number of elements and cost of the phased array quite a bit. But if it is a wide scan arrays, like if you want to scan 70 degrees or 80 degrees, you want to reduce the scan loss, so you want to keep the square lattice, which gives you better performance. So it depends on the application. So here you have basically this is the receive phased array. We have some filters to reject the transmit signals because you don't want to saturate the LNAs. You have LNAs, and then you have if you have M beams, you have to divide that into 1 to M. Then you have phase shifters and attenuators, variable phase shifters. They're all at low level so that the losses won't affect the gain that much. So they're after the LNAs. So you don't never put them before the LNAs. And then you combine N to 1 because you have N elements. You need to combine all of them to create beam 1, beam N, beam M. So in advanced EHF, I showed the video. It has about 8 beams, spot beams. So you have to divide 8 ways. Of course, advanced EHF, we didn't do it RF. We have to down convert to IF, which is like a C-band. And then we have a digital processor to go through. So we don't have the variable attenuators and phase shifters. Everything is done digitally. So requirements, gain, directivity, scan coverage, beam width, polarization, side lobes. So all these factors are important. So then your design parameters are choose the array lattice, element spacing, depends on the scan, how far you're scanning. Grading lobe location, you want the grading lobes, but you want them outside the coverage. The reason you want the grading lobes is if you design without the grading lobes, I think your element spacing becomes small and the cost of the phase array becomes very large. For geostationary satellites, you have seen the coverage is only plus minus 8.7 degrees. So when you have that, you can put a grading lobe at about 12 degrees and increase the spacing between the elements and then reduce the number of elements. So unlike radar systems, I think we want the grading lobes. And these are some equations. You can refer to one of my papers or the textbook. You can get you can calculate how many number of elements you need based on the required directivity and the element directivity. So sometimes directivity you have to take into all the losses, cross-pore losses, the scan losses, the insertion loss between the amplifier element, etc., some implementation margin. So these complex systems you don't design without any implementation margin. Typically, we use a minimum half a dB implementation margin. So sometimes even 1 dB, depending upon the complexity of the system. And then you can calculate efficiency very easily. So I don't go through that. This is the phased array actually on the right side. The advanced AHF uplink phased array at 45 gigahertz. You can see it has about 400 horns. The horns are about 3 wavelengths in size or spacing. What you see on the top is a thermal cover protected from temperature variations. So this is limits the thermal change to the elements, and then any heat generated through LNA is taken through heat pipes and then dissipated into radiator panels. So you can see them. The whole thing, then you have a digital processor at the bottom. So that's basically the crux of the whole. It has anti-jamming capability and a lot of other features, different waveforms. Pardon me? There's a paper published in AP Magazine, April 2020. So this is one of the interns, I think, he's a pretty bright guy from UCLA. So we sort of, he worked with me for almost 3 years. So he's very, very sharp guy. So it shows some patterns. I won't go through the both side, and you can see the grading lobes there. So, but they're falling outside the coverage region. So here, worst case 13.5 degrees. So grading lobes is almost like a main beam, but at reduced because the element roll off actually reduces the level. So, and some parametric curves, I think, useful to design the phased arrays. So you can actually design the phased array. People think it's very tough, but if you have a calculator, you can do it probably within half a day or so. So of course the design is easy, but then implementation you have to be careful. So that takes a bit of time. So this is the advanced AHF phased array. You can see the size there, about 18 inches or so diameter. And there are other phased arrays which are octave bandwidth and multiband. The one at the bottom, you can see this a conical notch. It can give from anywhere from 1 gigahertz to 18 gigahertz. So very wide band. So this is another one which is a multi-layered elements on the top right hand side. You can see the unit cell. It has 2 horizontal elements and 2 vertical elements. So you can actually change the polarization. It can give you VP, HP, or LCP, RCP. So hybrid antennas, it's a combination of reflectors and phased array. People try to do that. I think people actually try to do confocal antennas and reflector arrays for communication satellites. I would say that it's a bad marriage of reflectors with phased array because it doesn't have any advantage. I think either use it's spoiling the good properties of the reflector with limited capability of the phased array. So I think people tried confocal antennas for a while. I think Bell System Technical Labs, Dragon has his original paper in 1982 BSTJ journal. But a lot of people tried to implement that, but so far you don't see any confocal system in space because it doesn't work. Reflector arrays, you don't see them as well, at least for communication satellites. I think it has applications for narrow bands like imaging or sensing satellites, but not for communication satellites. So imaging reflectors are used. I think they're used for mobile and military applications quite a bit. They have some advantages. This is how the block diagram. So this is a reflector. It has number of elements. Say in this case about 37 elements. So it has polarizers, the filters, and then 1 to M, then LNAs. So if you use like 37 elements and 37 element beams, your efficiency is going to be only 15% because you don't have the proper illumination on the reflector. Then if you combine 7 of them like that, 1 to M, So you can get about 50% efficiency, but that's not all enough for our application. So we go to the third level and then digitally combine. So what we do is we have a septet when you combine the beam with 7 elements. So the septet beams actually we combine. So then you have a proper illumination and get about 80% efficiency. So this is all done digitally, so it doesn't cost you much, but that's the way. So every time I think you want to do is check the antenna efficiency. If you're not very close to 80%, then you have to go and redesign. You don't have the proper design. So here I show you some recent developments for air and ground applications. This is mostly done this year. Probably some of them are pretty fast, I think, for proposals, and some actually we have a contract from AFRL and US Defense. So here what I want to say is the wisdom from Vedas. I think we think that we are very clever and we are knowledgeable, but we are nothing. If you look into over the years, what I think we learn mostly from our past, and we contribute very little so that the future can learn a bit more. So it's all incremental process. So I think if we don't have the knowledge from the past, I think whatever I think we are doing is not very good. So I think that knowledge is very important. So that's the reason I think we read a lot on the past papers and what people have done. So that way we don't start from scratch. You learn from what other people have worked and then you try to improve on that. So it's a combined knowledge. It's not an individual knowledge. So this is one application, COTM, communication on the move. It's for ground application, where a soldier, I think, is in the battlefield and he wants to communicate with the satellite in one frequency band, with aircrafts with other frequency bands, and with other local other soldiers and headquarters with another frequency band. So there are actually 4 frequency bands. So initially we looked into phased arrays, which was the initial approach. Then it requires 4 phased arrays because it's narrowband, and then it's very expensive. So each one costing about $3 million and weighs heavy and dissipation because soldier has to carry it. So you cannot dissipate a lot. So we came up with this petal reflector design. So it basically has quad band. It has K band, KA band, KU transmit, and KU receive. So you can see these pedals are very, here the mass and cost are very important because mass soldier can carry only limited weight when he's in the battlefield. So there's a lot of emphasis on reducing the weight. So we don't make a solid reflector. So we make out a pedal, which is very lightweight Rexolite material, and we metalize that once we make. These 6 petals are actually screwed to the common base of the reflector in the battlefield, and when it's not in use, they're stored in a small suitcase like this. So you can see the center geometry, and then is the feed is the crux of the problem. So we use a dual reflector system with a subreflector, so that the feed is very close to the vertex of the feed, and everything is compact. So we use F over D of 0.25 to 0.2, so to reduce the whole envelope. And so the actually supports 4 frequencies: KU transmit in 14 gigahertz, KU receive at 15 gigahertz, and K band transmit and receive at 20 gigahertz, and Ka band receive from satellites at 30 gigahertz. So all of 4 frequencies are supported by the feed and its components. So you can see the patterns actually at 20, 30, and 14.5. So it's mounted on a very lightweight gimbal mechanism. To access gimbal, it can scan plus minus 90 degrees in elevation and 0 to 360 degrees in azimuth. So there's a COTS gimbal available from manufacturer in US. So very inexpensive, to $2,000. And then it's mounted on a graphite tripod structure so that the soldier can carry it independently. You can disassemble and carry separately. So key considerations here is mass, cost, and storage. whole mass is 10.1 pounds, whereas if you use 4 phased arrays, the mass is about 36 pounds or so. A single antenna replaces basically 4 phased arrays. So we have actually a patent pending on this technology. So this work is done probably in 3 weeks. So this is the block diagram of the feed. You can see the feed is a quad band smooth wall horn with flares to generate high modes. And then it takes out the KU band first, which is the lowest frequency with a symmetrical 4-port junction. And after that, you reduce the size of the waveguide so that all the low frequencies are cut off and then high frequencies propagate through. And then in KA, you add a diplexer there, so to separate the 2 frequencies. And then at the KU band, you combine all the 4 through H-plane Ts, and then finally with a hybrid coupler to generate RHCP and LHCP signals. Another thing here is they want to change the polarization, either left hand or right hand. So the corrugated polarizer we have here, so it has 2 rotary joint, one before and one after, so that we can manually rotate it and use any polarization we want between either LHCP or RHCP. So this is the block diagram you can see. So gimbal, and then there's a cable actually running through. So whole thing weighs about 10.1 pounds. This is another application. It's very wideband, ultra wideband, 1 gigahertz to 60 gigahertz. So this one requires very compact. I think initial requirement they gave is 24-inch by 24-inch. It has to fit. So if you try to use the typical technology for ultra wideband is the Vivaldi type designs. So if you use that to get the gain what they need, you need about 10,000 elements. It's very expensive and very heavy, so you cannot use that. So what we have done is we have segmented into 3 different frequency bands. Low band going from 1 gigahertz to 8 gigahertz, and then medium band 8 to 20, and then high band 20 to 60 gigahertz. So you can see the directivity versus frequency. We can get as high as 43 dBi at high frequency, and low frequency the requirement is 5 dBi. I think minimum we get is 6 dBi. So it's very compact, and our spec for the mass is 50 pounds, so it's about 45 pounds and the low cost. And we just submitted the proposal 3 months back, and we just learned that last month we were selected to do this. So this one is actually UHF to millimeter wave. I think it has digital TV, 3G, 4G, 5G, and future 6G communication going up to 100 gigabits per second capacity. So it has different waveforms as well, GSM, wedge, WCDMA, and other types of waveforms. So I think we got the contract, so starting from January, we have to work on it to make the hardware and deliver it. This is a missile application, vehicular antennas. Northrop Grumman got selected to develop next generation missile systems called GBSD, ground-based strategic deterrent system. So they want to upgrade all the missiles. So they typically work at L1, L2, and S band. So it's almost $65 billion, and with options, it's almost $100 billion. So it's the biggest contract we got. But the problem is the earlier designs, what were used on Minute Maid, they won't meet the phase variation spec. It used to have 20 degree per degree phase variation, but now they sort of want less than 2 degrees. So that's almost 10 times more stringent. So we don't have a design right now. I think we are developing antenna design, I think meeting those requirements, which is in progress. So I can see here the past design, when you have 2 patches like this, 180 degrees apart, you can see at 90 degrees they sort of dropouts. So this is not very good. So I think from here we want to go almost very uniform phase patterns. So these are the phase plots, or amplitude plots are also very similar to that. So how to do that? So first, I think we want to make sure that our simulations and designs are correct. So we made a 2-element cylinder representing the missile structure. So we have done pretty good analysis, and we tested it, and we showed that good agreement between our design and measured results. So customer is happy. And then we are trying to a novel approach to design to meet the stringent phase variation spec. So it's called a sector antenna. So what it has is basically 6 sectors. So you can see within the sector, there's about 6 elements. So there's no BFN. And the height is very small because we use reduced waveguide size, and we also use ridge waveguide to reduce the size and mass. So the thickness is only about less than 0.3 inch or so. So, and then you can see the slots. So you have only one input, and then the slots are designed so that everything is uniformly illuminated, and no power is left at the end. And if anything is left, actually we have a load so that the reflections won't come and disturb the patterns. So it will be absorbed. And it will be mounted, 6 sectors will be mounted around the body of the vehicle. And the cables actually take it to, and then we combine them through 6 to 1, and then we have other communication equipment. So this is done at L1, L2 GPS frequency bands, and also S for TT&C S band. So it has advantage low mass because there's no BFN. It's low cost because it's lightweight. We don't want to use any dielectric because the temperatures can go as high as 1200 or 1300 degrees C when the vehicle is launched. So antennas have to survive those temperatures. So we don't want to use any dielectric there. Of course, it has a radome. So when we design, the radome effects are taken into account. This is how the sector looks like. 5 slots per sector. There's no BFN. Everything is metallic. There's no issue with ESD or thermal stability, and also insensitive to tolerances. So when we do that, this is what we get. Actually, we are not there yet. I think we are right now at 2 degrees per degree spec. I think we are meeting. I think we want to improve some margin. So we have some development to go through next year to reduce this to around 1.5 or so that we can give some tolerances so that we can make them very cheap. These are thousands of antennas are needed. So we have US patent pending on this technology. So PFC, another program, Protective Forward Communication. So this is where the soldier actually communicates with headquarters through BLAWs or aircraft with the line of sight or with the local area with other soldiers. So we designed actually, again, it's a very lightweight and very omni type antennas needed. At the same time, for other applications, you need 10 by 10 phased array for K-band. So we did the pen cap antenna for UAVs. So you can see 2 of them on the 2 bottoms of one is on the bottom side of one wing, one is on the top side of the other wing. So these are 2 pen cap antennas providing, each one providing 2 pi steradians so that you can cover the full 4 pi steradians. Size is very small. It's 1.2 inch by 0.6 inch in height. Mass is very low, about 60 grams. So I think when we designed these, I think they didn't have UAV the customer was not thinking about UAV, but when they saw this, they said, yeah, we can have UAV applications. So we modified the design. For UAVs, actually, we need to minimize the improve the front to back ratio. So we have a shaped ground plane here. And then you can see the patch is a single fed patch with notches in the 45-degree plane to generate the circular polarization, very simple structure, but it has a radome cover on top of it so that it can It can live with the wind speeds which in the aircraft is going through. And then we have very good agreement between, this is first time try, we didn't sort of design and tried it very quickly. So it's a first time success and the customer is very happy. You can see on the bottom the dielectric on top of it, and this is basically copper. And then when we make them in quantities, we need to make about 3,000 or so. We use aluminum to reduce the cost and reduce the mass as well. And then you can see the connector on the bottom. So it's a very simple design, but it's some of the components are 3D printed. So we can do that 3D printing as well. Very good agreement between measured and computed as well at different frequencies. Bunker, this is very important because this has other feature. It has to be deployable as well, and it has, soldier has to carry it. It's a K-band, RHCP, but it has to have 4 pi radians coverage. Minus 10 dBi is the spec, over 95% coverage. I think we made that with 4 dB margin or so. So it's mounted, it will be on the behind the helmet of the soldier when it's in the halt, and it's deployed about 12 inches above the head of the soldier so that it doesn't impact the head of the soldier, so the radiations are low. So mass is less than 250 grams, and you can see it's inverted F with a radome on the top. It's all metallic. And this is how it sort of folds and unfolds. So you have here the hole where you can hold that material, and what it has is the actual antenna is on the right hand side. You can see the bunker antenna in blue, right hand side top, and then you have a connector at the bottom, and then you have a clip actually, and you just remove the clip and then hold here in the handle and then fold it to there are 2 stops actually, put in 2 blue. So move it to the another stop. So then it sort of unfolds and becomes like this. So and then the conduit, this is actually conduit. So that this provides the flexibility. And then the region between the conduit and the handle is very important because we have to seal it against the atmosphere. So nothing water or snow or ice or dust cannot go in there. So you have to be careful. And actually cable is inside. So RF cable actually goes inside, and it's a connector is on the outside. So it's very simple mechanism, and soldier can, when it's lying down, it is behind the helmet. And when he's standing, I think it's deployed by about 13 inches above the head, 13 inches from where it is. So I think we made about 4 of them. We gave them, so they're doing some field trials now. This is how it looks like when it's made, everything made without the antenna. And I think I have a video here to show the deployment. And then you can hold it and fold. It's very simple, lightweight, and I think customer likes it, but they probably field testing and give us some feedback so we can change the design as needed. These are the patterns. I think didn't want to go through. Modular phased array for this is a 10 by 10 phased array. So we tried to use everything here, say 100 elements. So combined through BFN. So then your number of ports for the digital processor is very, very large. So DC power is going to be high, and then it's expensive as well. Case 2, we tried to make a subarray 2 by 2 and connect with a 2 by 2 BFN, and then reduce the number of amplifier and of inputs to the down converter to 25 from 100. So it has some problems with grading lobes. So we selected case 3. So where we have 2 by 2 subarray, but then it has phase control, phase and amplitude control after the LNAs, and then you have a combining network, and then you have 25 subarrays to go into down converter and BFM. This is how it looks like, the element pattern, subarray pattern, and then the final phase array pattern with the different amplitude tapers, uniform, 6 dB, 10 dB. I think this you can either calculate very easily, or you can plot and see what is the gain impact. And of course, when you go to 10 dB taper, I think gain impact is 2.8 dB, but your side lobes go from 13 dB to 23 dB, 10 dB improvement. So this is the 60-degree beam. Actually, you can see on the left side, minus 60. That's where the beam is for design 3. So case 3, which is same as case 1. And then actually you can see the grating lobe is higher. That's because we have, but that's okay. I think as long as we know the position where we need to scan, so even if the grating lobe is there, we're not bothered too much about it. So this is being fabricated, and we tested, and we have pretty good results. And whenever you design a phased array, you always add one outer ring. So here 10 by 10 is 12 by 12. So outer ring is terminated so that all elements look similar. Otherwise, edge elements look differently compared to the central elements, and you lose some gain. So you don't want to do that. Always have either one or two edge ring of elements at the edge match terminated. So in this case, we want to keep the mass low, so we just have one ring of elements match terminated. So have pretty good pattern. It can scan up to 80 degrees. This is another, I think I am almost done. This is the advanced ground antenna. I think this is what it used to be on the left-hand side. So, I mean, this is typical design for any ground antenna. You have, here we have L and S band feed, and we have KA horn. It's a dual reflector system. Your subreflector is a frequency selective surface. So it is transparent to L and S band signals, but it's reflective to K band signals. That's how the FSS works. And then you have struts here, 4 struts. So this is 5.4 meter reflector. Now they want to, AFRL want to upgrade all the ground antennas from, I think they have up to from 3 meters all the way up to 13 meters. So there's hundreds of them. So they want to add 6 more frequency bands. They added another L band, X band, K band, lower Ka band, and we came up with a design where much simpler actually. We don't need FSS. Of course, if you have FSS, you can't add additional frequency, and FSS is a lossy surface. And then we don't need any struts, because struts, we know that struts will block and scatter. So you lose a gain of about 0.6 dB or so due to struts. So we eliminate the struts. So you have a subreflector supported by a feed cone, and then it's a dual reflector system, but no FSS. And then FSS L band, you have a long cable, so you don't have that cable loss. So as a result, at the basic frequencies LS and Ka, we get about 1 dB more gain because of no struts and also no cable, and you don't have FSS loss. But then the feed is tricky. I think we came up with a multi-cavity type feed system to cover all the frequency bands. And we completed the design. I think they gave a contract to make 3 feeds, one for 5 meters and 2 of them for 5.4 meters. So we're in the process of starting the fabrication. So this is how it looks like. So we have basically 3 apertures. Aperture 1 is 19 to 45 gigahertz. Aperture 2 is 7.5 to 15. Aperture 1 is the low frequency, 1.75 to 2.3. And added complexity is it has tracking at Ka band and other frequency bands as well. You can see the block diagram. It's very complicated. So it's a cluster of coaxial junctions. So the central feed is waveguide. The rest of the two outer ones are coaxial feeds with 4 feed points, you can see. So it has a lot of hybrids and how to isolate these different frequency bands by filters, diplexers, etc. We're designing the hardware components right now. And patterns are pretty good. We get about 1 dB better at standard bands. And this is the high frequency satellite. I told you the congestion in the geostationary satellite orbit. So this is the experimental satellite we built for US Air Force, and it's going to be launched next month. So it's a very simple, it's a 2-horn cluster on the satellite. It transmits, satellite only transmits it. So, and the ground station receives it. Ground station is ADE type design. So it's a 24-inch reflector. So it's 2 horns, but initially when they gave, they didn't give us the orbital slot. They said anywhere from 80 degree west to 120 degree west. So how you design, if you design for wide orbital arc, then your coverage area becomes very large and your gain drops. So what we did is we used the roll and pitch biases of the spacecraft. So we use only 2 horns. The horns are very large, they're about 8 lambda. So when you combine, of course, grading lobes come, but they fall outside the coverage. So we don't care about it. And then by using, actually, we don't use the roll bias. Roll is fixed about 6.5 degree above the equator. And then only by pitch biases, they're controlled with the different waveguide sizes. So, when you use the pitch biases, your whole area becomes small, and then you get the composite area very small, and you get the proper gain. And then this is actually, we have a contract to build actual satellite. The previous one, we call it Whiskey T. Previous one was the experimental satellite. This is the actual satellite. So this is covering 71 to 76 gigahertz, and on the transmit side, 81 to 86 gigahertz on the receive side. So it's a 36-inch reflector, ADE type design. So it's a diplex feed. So it covers both the frequency bands, and you can see the gain. So feed assembly is a horn with a septum polarizer, diplexer. We need only one polarization, so we use diplexer. So we have test couplers to test when everything is integrated and the satellite is on the ground. We have to test how much power is going through transmit and what is the G over T for the receive. So that test we have to do in T-back chamber. So where you cycle over hot and cold temperatures, and then monitor the other system parameters like group delay and other things as well. So that's why test couplers are important. And contoured beam satellites, you can see how the spacecraft, how all the reflectors are mounted against east and west panels, 4 of them, 100-inch. And then there's one antenna on the nadir as well. So all of them will provide service like corner shape, and also other countries like Turkey. You can see one shaped coverage, actually it can cover both Turkey and South Africa. So this is one design we have done. And you can see the bicone here. We have a command bicone on the top, which is high frequency, and the telemetry command on the bottom, which is slightly low frequency. These are all Ku band. It provides actually azimuthally symmetric pattern, but with certain elevation angle of plus minus 30 degrees, depending on the cone angle of the bicones. This is the large deployable mesh reflector. I think they can go up to 22 meters. Northrop Grumman makes all these mesh reflectors. Harris also makes, generally our standard is 12 meters, 18 meters, and 21 meters. So Harris also has similar thing. So the mesh is gold molybdenum wires, actually. You can see on the bottom right. So depending on the number of openings per inch, at the L and S band, I think you're generally okay with 10 openings per inch. At high frequencies, you need about 40 openings per inch. So we are developing at high frequencies also, very large reflectors. And this is the video again of NASA SMAP payload, for which I think we supplied the reflector. NASA did the, I think, design that. So you can see the reflector is actually in the the boom is actually deploying now. The cylinder where you have the 16 reflector. And you can see the feed with the thermal cover on the deck. This is after 2 weeks of launch. I think once the solar panels are deployed, you deploy the reflector. After 2 weeks, it doesn't cause any imbalance on the satellite body. And it's fully becomes like a parabolic reflector, very close. So it has a back. So it rotates at conical angle of about 30 degrees. So this one is a low Earth orbit, about 80 above Earth. It rotates at about 15 p.m. The complexity of the antenna, the mesh reflector and the feed and the rotating mechanism. So these are pretty complex systems. So when you design these antennas, you have to make sure you involve the mechanical guys, the gimbal guys, and system engineer. You have to work with all of them. Then only you can provide the right payload, right antenna for the payload. So this is actually 20 kilometer swath as the satellite moves around. I think this swath spreads around the poles, thanks to JPL. So multiple beam antennas, I think we talked about shaped beams, but they're limited capacity. So if you want high throughput satellite, so you divide the coverage into number of spot beams, in this case about probably 60 or so. So then you divide the spectrum, which is 500 megahertz into four cells, 125 megahertz each, and use the cell 1 on alternate beams, 1, 3, 5 for a 4 cell to use, and cell 2 on 2, 4, 6 alternate beams, cell 3 on 10, 12, etc., and then cell 4 on 11, 13. So that way you cover all the beams. So what happens with that is your beam size is reduced quite a bit, 0.6 degrees. So your gain improves from 30 dBi to 46 dBi, almost 15 dB improvement in one both uplink and downlink. So total you get about 30 dB gain, improved link. And more importantly, you get a spectral use factor of 15. So since you're reusing them 15 times each of these cells, so your effective spectrum becomes, instead of 0.5 gigahertz, it becomes 7.5 gigahertz. That's where you get the capacity. So this is actually, initially we did for 60 beams. Now I think we did 400 beams, I think, which gives very close to 1 terabits per second. Another supplier is also making Viasat. They're developing a system where they go beyond 1 terabits per second. So these are the frequency reuse schemes, different frequency reuse schemes. Then you use multiple apertures. If you use a single aperture, your gain is small. So you have to use multiple apertures along with multiple beams, either 3 or 4. 4 is typical. So you can put symmetrically 2 on one side, 2 on the other side, and use all 4 apertures. And then you can increase the feed size almost twice compared to a single reflector. So that's where you get improved efficiency of close to 80%. So this is for BSS application, broadcast satellites, where initially we used to have in 1990s, we used to have only national channels. So like ABC, NBC, and CBS. So now everybody wants local channels. They don't care about national news. They want to know about their local news. So then they divided all US into 216 designated market areas, they call it. New York is top ranked based on the population, and Los Angeles is number 2. Number 3 is Chicago. San Francisco is number 5. So this Directivity came to us, and then they said, if you cover top 60 DMAs and you have the contract. So the design is a bit difficult here because you're on the East Coast, you can see all the DMAs are congested because their very density of population is high. And Midwest, I think density of population is low. So same for the West Coast as well. Density of population is high, but not as dense as the East Coast. So we use 4-cell reuse scheme. You can see different colors: red, green, black, blue, etc. So all the reds, you can see they're different sizes because we have to cover one beam, number of DMAs. So you have to make sure that between the reuse beams, same color, there's no side lobe isolation. You get the proper side lobe copolar isolation. So beam sizes are different, beam spacings are different. So when you try to do with, people try to do with the TICRA analysis, so it was taking some months and months because you can never. So we developed a Gaussian beam analysis, and I think they came to us, and then we said we completed the design in probably 2 weeks, less than 2 weeks when I was at Boeing, and I showed them the layout, and they said we covered all 216 DMAs, and they were really surprised, and I think we got the contract and we delivered in 24 months, the complex satellite. Of course, this has local channel broadcast. At the same time, there's national channels as well. So probably this is the most complex design I ever did, at least on the commercial side. There's some work on GPS. I won't go through. It's a advanced next generation GPS with 37 element array, providing spot beams and at the same time coverage beams, area coverage, global beams. So you can see the satellite payload, how it's mounted on. So it has 3 frequency bands, L1, L2, and L5. So we have a triflexer behind each element. So that's a key component for this. And then other thing is the phase center has to be unique. It cannot move with the frequencies. So there's a stringent spec on that. So we designed the element such that the phase center doesn't move. It's a unique design of the element. It's very short, actually. You can see polarizer mostly. And then from the polarizer, the radiating part is very short. So the phase centers are actually, yeah, you can see it here on the bottom left. At L1, L2, and L5, 3 different frequencies. They vary only within 0.05 inches. So we'll get very good phase response, which is important for GPS because that determines the accuracy on the ground, whether it's 1 meter or 10 centimeters or etc. So you can see the triplex filter performance, and then it has high power handling also. So when you design these, you have to make sure that it handles the power, and also PIM is very critical. So all these interfaces, top left is a triplex design, low loss triplex. So some scientific missions I won't go through. This is Mars. I think it's 3 meter. It has X and Ka band. You have Galileo reflector, which is built by Harris, but it didn't deploy when it's first launched. So they have to take it very close to the sun, heat it up, and shake the body. So then it deployed. So by the time it's deployed, there is no fuel left in the spacecraft. So life is very short. We saw the SMAP and Voyager mission. So 3D manufacturing, I think that's a lot of people are working on this. So for space, I don't know whether how far we'll, but we are trying to develop some components using 3D printing technology. Of course, with the dielectric you can do, but we can't use the dielectric in space. So we have to do with metal. So this is aluminum, magnesium, silicon magnesium alloy. And it's a bit when you do the 3D machining, I think losses are high because the surface roughness is, it's very rough. So we are looking into new alloys which can reduce the roughness and reduce the insertion loss. So this is actually 3D printed machine from Germany, SLM. So this is the state of the art right now for metal printing. So won't go through, but we build a filter and actually it works, except it has more insertion loss as expected. Other manufacturing is CNC, machining, milling, lathes, EDM, and electroforming. So most of the components we do at high frequencies are electroformed because you can get very tight tolerances of about maybe less than half a mil, 0.3 mil or so. So very tight. So passive intermodulation, I talked about briefly. When you have high power carriers, two of them like transmit carriers, F1, F2, they beat against each other and create intermods. So depending on the order of the intermod, I think your PIM levels goes down. And if these intermods fall in the receive band, I think that's very sensitive. So it depends on the order. If it is 7th order or low, you have to, or high, you don't need to test. But anything 7th order or lower, you have to test it. So when we design, we have to make sure that we select the frequencies so that your PIM order is probably 11th or 13th or something higher. But sometimes it's not in our hand because frequencies are fixed by the customer. So we have to measure. When we measure, this equipment is very expensive. So typically this is what you get as you run through hot and cold, different cycles. So you can see the blue curve is the average PIM and blue color is the worst case PIM and the red is the average PIM. So our spec was minus 132. I think we are measuring almost minus 138. So other tests are you have to do like thermal test, TVAC test. TVAC is a thermal vacuum chamber. So high power test you have to do, make sure that it can handle the power. Sometimes we do by analysis. So if we have enough margin like 10 dB or 9 dB, I think we don't need to do the test. So we can show by analysis. Polarization check, that's very important. We do it several stages, PIM tests. So between these tests, you have to do functional to make sure that return loss didn't change. Radiation patterns, of course, we have to do before these tests and after as well. And then mechanical, I think qualification we have to do with vibration, because when you launch, I think high levels of vibration go through antennas. So you have to make sure that they can withstand. Acoustic tests we typically do for large antennas, not for small antennas. And EMI, EMC tests we have to do at the end when everything is integrated together. So some range tests I think we have to do. So we have about 18 different ranges. The biggest is 50 foot by 50 foot planar near field. We have two 12 foot by 12 foot planar near field. Bistatic range to characterize the frequency selective surface, the thermal covers, etc. Material qualification. Spherical near field, we need to test the omni type or low gain antennas. And compact range, we have 6 foot quiet zone. So we do some pattern tests in the compact range and system level tests as well. And anechoic chamber to test the small antennas like feed horns, etc. So academic training, I think that's very important. I think there's a significant gap between academic training versus real world engineering. I think it's not just in one country. I think we're seeing it globally. I think we're seeing in US quite a bit there. So the question is, are the universities providing proper training to future engineers? A lot of them, I think in the universities, they're happy to use HFSS, CST, FICO, but in real world, it's a TICRA grasp because most of the antennas are reflector based. SHAMP, which is also TICRA software, Cobra, TICRA software, Mission, CST. Savant is for aircraft applications where you want to sort of see the coupling between the antennas and placement of the antennas on the aircraft. Spark 3D is developed by Spanish people. You can actually detect the multipaction very easily. You can analyze them very accurately. So I think all these softwares are real world. And hardware, I think I see most of the publications, papers coming from universities are patches, slots, reflector arrays. And I think in real world, I think you want horns, reflectors, at least need to include. I think I'm not saying that patches we can't use, slots we can't use, but majority is the horns, reflectors, space, air for all ground antennas. So I think there seems to be a gap between training, I think what people get. I think some engineers we hire even from UCLA, we can't use them directly. They're all biased to run the software and show some results without knowing the hardware limitations. So I think that's the reason we basically hire like 2 guys in this case every year. I think this is the picture it's shown is what we have is Mentor Prodigy program, which is sponsored by the defense, US Defense, D&D. So this is a 3-year, every 3 years, I think we can, every year we get to work with a university professor, in this case, Cal State University, Los Angeles. So that 2 interns they give every year. So we train them, they work with us. We tell them what to do, and one electrical, one mechanical mostly. And then we have a small company. They want small companies within US to sort of design and produce the hardware for them. So we need to train the company as well. So it's a three-way collaboration. So it's actually working very good. I think last 2 years we actually hired all the interns. Actually, once they finish the interns, I think we hired them so they can actually work on real-world problems. So that's a very good program, and hope others also in India. I think you have some programs like that, maybe in IIST or some with ISRO and the DRDO collaboration. So India has actually a great talent. I sort of, whenever I come to India, I feel that the students are much more motivated and want to learn a lot. Here, I think people sometimes may not be that motivated. So I think you have very good talent, and I think definitely the support of the industry, I think you guys can do wonders. So ISRO and DRDO only have very good ground observatories, RRIs, Raman Research Institute, TFRL, Samir, etc. A lot of companies which hire antenna engineers. I think it's very good. And the university, industry, government collaborations help to remedy the situation. So something to think. Maybe from IST side, I'll ask Professor Dodwal and other seniors to look into this, to train the engineers. Conclusion, antenna is very exciting field to work and innovate. Understand the basics first. I think nothing, I think I can't stress more than basics here. So as an engineer, I think you have to be very strong in basics. So that's why you have to learn from your process very well. And if you don't understand, you have to ask them and challenge them as well. So apply, I think learning is not good, only learning. So you have to apply to real world problems. So that's where I think this internship and working with companies will help. And then once you join the company or industry, then you have to develop concepts. And once you become a senior, you have to think outside the box. So acquire critical skills, hardware knowledge, software, mechanical, manufacture, system engineering, customer understanding. All these things are important. So don't just look into your own area. Try to sort of work with other areas also, learn what people are doing and what is important for them. And more importantly, work with passion and enjoy your work. It makes a big difference. So whenever you go to work, I think in the morning, you have to go with a lot of enthusiasm. You can't just say that, oh, it's another day. So that's not very good. So I think you have to be self-motivated. Innovation should be the daily routine of engineers. So without innovation, there's nothing. So all the companies, I think, thrive on innovation. So they put the IP portfolio very high in their culture. So innovations or patents, trademarks are highly supported by big companies. So engineers need to innovate products useful to the company. So I think I leave with this quote: innovation distinguishes leaders from followers. So you have to be a follower when you're young and join the company. You need a mentor, and you have to follow the mentor. But don't follow him for a long time, then you cannot do anything yourself. After some time, you have to divorce your mentor and start working your own, and you have to develop mentees. So, and you have to lead your organization. So this is the quote from Steve Jobs, late Steve Jobs, ex-CEO of Apple, which is very apt, I thought. Then at the end, I think that's all my talk, and I'll leave with this video, if it works.
B-2 was originally intended to carry nuclear bombs deep into Soviet territory if the Cold War had ever turned hot. Its airplane stealth systems would enable it to be undetected by Soviet radars. The B-2's long range meant it could fly deep into enemy territory and return home. With the collapse of the Soviet Union and the end of the Cold War, the B-2 has been used as a conventional bomber. Its debut during the Kosovo War in 1999, and has since flown sorties in Afghanistan, Iraq, and Libya. More recently, the B-2 has been placed in bases in the Pacific as part of a strategy to deal with potential threats from North Korea. Here's why it's one of the most aircraft in the world. The B-2 bomber was shown to the public for the first time in 1980, for the end of the Cold War. Its stealth capabilities were virtually unmatched. The B-2 can carry 16 2004 83 nuclear bombs, but its official limit of 40,000 pounds of ordnance means it can carry a massive amount of precision-guided munitions. The B-2 has a max range of 6,900 miles on a single tank, but every refueling gave the bomber on one bombing mission. Two B-2s flew a 34-hour round-trip mission from India and were refueled in the air 15 times. Each of the current U.S. in service are named after states. Here, the Spirit of the B-2 in July of 2012. The B-2 is a flying wing aircraft, so it has no fuselage or tail. High structural efficiency and generates more lift than other fixed-wing aircraft. The B-2's max are 0.5 or 630 miles per hour.
Okay, all the B-2 aircrafts are. Right now, we are building the next generation B-21, so we have a big contract on that as well. So a lot of R&D is going on how to improve the B-2 design to B-21. So that's probably a 20-year contract, and R&D, I think, supposed to finish in 5 years. So development. So a lot of people are working on it, including myself on the antennas. So that's all. Thanks very much for your. I exceeded my time, looks like.
Thank you, Dr. Rao, for sitting late night to share your wisdom with us. It was a very inspiring and informative talk. You discussed the complexities in the design of satellite antenna systems, and also you have stressed the need for collaboration between academia and industry, which we in the academia will be seriously look into. And you have also given a message to the, especially the students who sometimes do only the simulation. So the need for knowing the fundamentals, which is very important. So there are some questions in the chat box, but I will request the participants to directly send mail to Dr. Rao, because due to a lack of time, I think that is what we can do right now. So once again, I thank the organizers for giving me this opportunity, and also I thank Dr. Rao